We just introduced Stokes' theorem. So one of the first things we should do is that we should verify Stokes' theorem in a relatively straightforward case. So verify Stokes' theorem for the vector field F is written right there. And S here, let me draw a picture. So this is going to be, so x squared plus y squared plus z squared is equal to 1. So this is going to be a part of a sphere. Z is greater than or equal to 0. This is going to be upper hemisphere right here of radius 1 centered at the origin. So the surface in question is this right here. What is the boundary curve? What is C? C is going to be the boundary here. That is C. This is S. So this is our job, is that we need to compute the circulation F along C. And then we need to compute a double integral of the curl. So I guess first we have to compute the curl. We need to compute a double integral of the curl of F over this surface right here. So let's go ahead and get to work here. So for the integral of F along C here, well, we need to parameterize the circle here. This is just going to be the unit circle center of the origin, the xy plane. So R of t is just going to be cosine t, sine t, and 0, where the parameterization t is running from 0 to 2 pi. F of r of t. Okay, we're going to plug this in up here. So that's going to be negative y is negative sine t. And then 2 times x is 2 cosine t. And then the coefficient here, x plus 0 is cosine t plus 0. So there is our f of r of t. R prime of t. So the derivative here is going to be negative sine t, cosine t, and 0. There's our r prime of t. What else do we need here? We need f of r of t dot product r prime. So f of r of t dot product r prime of t. So this dot this would give us negative sine t times negative sine t is sine squared t, plus 2 cosine t plus cosine t. So that's 2 cosine squared t plus 0. So, okay. This is going to equal integral t runs from 0 to 2 pi of this expression right here, sine squared t plus cosine 2 cosine squared t dt. I'm just going to write down the final answer here. You get 3 pi after doing a little bit of trigonometric manipulation in here. Okay, so we've got 3 pi. Okay. Next step is that we need to compute this side of Stokes' theorem, which means first that, well, we need the curl. Okay, let's get to work on the curl. The curl of F. So this is going to be, so the I hat, j hat, k hat, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, negative y, 2x, and x plus z. Okay, so this is going to be I hat times the partial derivative with respect to y of x plus z, partial derivative with respect to y of x plus z, that's 0, minus the partial derivative of z, minus partial derivative with respect to z of 2x, that's also going to be 0, minus j hat times the partial derivative with respect to x of x plus z that's 1, minus the partial derivative with respect to z of negative y, that's 0, plus k hat times the partial derivative with respect to x of 2x, that's 2, minus the partial derivative of y here with respect to, partial derivative with respect to y of negative y, that's negative 1. Okay, so what do we end up with here? 0 I hat minus j hat plus 3 k hat. Okay, so this is the vector that we are integrating here. We need to write down our surface integral calculations here. How do we parameterize the surface? So r of phi and theta ends up as, so we should know this here, cosine theta sine phi, sine theta sine phi, and cosine phi. These are r of theta, phi comma theta. And the corresponding normal vector is going to be, let's see here, it's just going to be the same exact thing, but with a factor of sine phi out in front. So cosine theta sine squared phi, sine theta sine squared phi, cosine phi sine phi. So all of this is just, we worked out last section. Okay, so then what do we need to do? This right here, this is the vector field that we need to integrate here. So common mistake now is that people, we need to do, plug in our parameterization into the vector field we're integrating, but it's not, but we don't plug in our parameterization into f because we're not integrating f, we're integrating the curl of f, and the curl of f has a constant. The curl of f is a constant, so we should write the curl of f, plug in r phi comma theta. At this point, we just ignore the parameterization here, and so this is just going to be negative j hat plus 3k hat. And then we need to do this dot with our normal vector here. So this dot this ends up as this times 0 plus this times negative 1. So that's negative sine theta sine squared phi plus this times this plus 3 cosine phi sine phi. Okay, so this is the integrand here. You're integrating negative sine theta sine squared phi plus 3 cosine phi sine phi. We're integrating this with respect to phi and theta. What are the bounds? What are the bounds here? So for theta, we're doing one full loop around the circle. But for phi, we're only doing the top hemisphere here. So from here to here, this corresponds, phi is running from 0 to pi over 2. So, okay, phi runs from 0 to pi over 2. Theta runs from 0 to 2 pi. And so here's our integral to evaluate. Here's our integral to evaluate here. As it turns out, this chunk here gives you 0. And then this chunk here gives you 3 pi. In the interest of time, I'm going to skip over the details. but that 3 pi exactly matches this 3 pi here as well. And so this is great. Stokes, we just verified Stokes' theorem. We got 3 pi here and 3 pi here for this setup here. And so we verified Stokes' theorem.